So welcome to the notes for sum and difference identities, and they're listed for you here on the front of the notes booklet, sum and difference identities for sine, cosine, tangent, and cotangent. And if you're interested in deriving these identities, seeing where they come from, I'll post a video for that that you can reference. But in these notes, we're just going to look at how to use these identities in order to evaluate trig functions for exact values of angles on the unit circle. So real quick before we get started, I want to look at this notation to make sure that everybody's clear on what this means. The cosine of the quantity a plus or minus b is equal to the cosine of a times the cosine of b minus plus the sine of a times the sine of b. And that minus plus is different from anything that we've seen before. So that's why I want to take a look at it first. So what this means is that if the identity that we're using is the cosine of a plus b, then we're going to use the minus sign when we evaluate the other side, cosine of a times cosine of b minus sine of a sine of b. On the other hand, if instead we use the cosine of the quantity a minus b, so we're looking at the difference of a and b, then when we do the other side, we're going to use the plus because that's on the bottom as well. So we would find the cosine of a, cosine of b, plus the sine of a, sine of b. So the order that the plus minus or the minus plus appears in the identity determines which one is going to go with the other corresponding. So you'll see that same notation here in the tangent sum and difference identity. The tangent of the quantity a plus b is in the numerator a plus, but in the denominator a minus. Right? Same thing for cotangent of the quantity a plus or minus b. So if you turn to the back of your notes booklet, before we get started using these identities, we're going to take a second here and work our way around the unit circle in radians, changing all the denominators to 12. Instead of 3, 4, 6s, 2s, 12 would be a common denominator for all these angles, which will make it much easier as we're evaluating these problems in the examples that follow. So if I'm starting at pi over 6 and I want a denominator of 12, I would multiply the numerator and denominator both by 2, and then that would give me a 2 pi over 12. Okay, then pi over 4, I would multiply by 3 over 3 to get 3 pi over 12. Then for pi over 3, that would be 4 pi over 12. Then pi over 2, I'd multiply the top and bottom of that fraction by 6 over 6 to get 6 pi over 12. And then 2 pi over 3, I would multiply the top and bottom by 4 to get 8 pi over 12. And then if we look, we'll see a pattern emerging. So it's 2, 3, 4, then we skip the 5 to get to 6, skip the 7 to get to 8. So that next one would be 9 pi over 12, then 10 pi over 12. Then we skip the next one, the 11 pi over 12 to get to 12 pi over 12. That's half the circle, which is pi. Then we'll skip the 13 pi over 12, making this next one 14 pi over 12. Then 15 pi over 12, 16 pi over 12. Then we skip the 17, and this next one is 18 pi over 12. Skip the 19, then we have 20 pi over 12, then 21 pi over 12, 22 pi over 12, then we skip the 23, and one full revolution is 24 pi over 12, which is 2 pi. So this would be our unit circle in radians, having changed all of the denominators of the special angles to 12s. So if you look at this next example, okay, we want to evaluate the sine of 17 pi over 12 using a sum identity. And here's that denominator of 12 that I said would be useful. So we want to find two angles on the unit circle that add up to total 17 pi over 12. So if we look back at the page before, the back of the notes booklet, I want to find two angles that add up to 17 pi over 12. So 17 would be 10 plus 7. Here's 10 pi over 12, but we don't know a value for 7 pi over 12. So 10 plus 7 wouldn't be a helpful way to break this down. But 9 plus 8 does add up to 17, right? 9 pi over 12 plus 8 pi over 12 would total 17 pi over 12, and we have values for both of those. 2 pi over 3 and 3 pi over 4 are both special angles on the unit circle. So those are the two angles that we're going to use, 2 pi over 3 and 3 pi over 4, because those total 17 pi over 12. So this is going to become the sine of 2 pi over 3 plus 3 pi over 4. Now looking at our sum identity for the sine function, which is right here, sine of A plus B, right, we're going to need to take the sine of angle A, and our angle A is 2 pi over 3, and we're going to multiply that times the cosine of angle B. So cosine of 3 pi over 4. Then a plus, and the cosine of angle A, and our angle A is 2 pi over 3. And then that's times the sine of angle B, and angle B is 3 pi over 4. Okay, so we just applied the sum identity for the sine function. Now, the sine at 2 pi over 3 is the y-coordinate at 2 pi over 3, and that's the square root of 3 over 2. Okay, we multiply that times the cosine of 3 pi over 4. Cosine of 3 pi over 4 is the x-coordinate at that angle, and that is a negative square root of 2 over 2. And we're multiplying those together. Then we add the cosine of 2 pi over 3, and that's going to be the x-coordinate at that angle, so negative 1/2. And then that's times the sine of 3 pi over 4, which is the y-coordinate at 3 pi over 4. That's a positive square root of 2 over 2. And now we want to simplify, so we're going to multiply root 3 times negative root 2. That's a negative square root of 6 in the numerator, and then 2 times 2 is 4 in the denominator. Plus, then negative 1 times the square root of 2 is a negative square root of 2 in the numerator. 2 times 2 is 4 in the denominator. And you're going to usually see these combined in your answers in the textbook. So since I have a common denominator, I can add my numerators to get negative square root of 6 plus a minus is minus square root of 2, and then that's all divided by 4. And that would be the exact value of the sine of 17 pi over 12. Now we're going to check that answer by making sure our calculator is in radian mode. And then we're going to evaluate the sine of 17 pi over 12. And that's going to give us a decimal approximation. Then we can compare that to the answer that we got, which was negative square root of 6 minus the square root of 2, all divided by 4. And notice that the decimals are equivalent. So that allows us to check our answer. The graphing calculator can't give us the exact value, which is why we need the identity, but it is really nice to be able to check and know that what you did was correct.